Alright, let's get started. Welcome to lecture 20, Robotics 311. Today we're going to go over like control for real. We're going to start control. So we're actually going to kind of talk about how controllers are structured. This is going to be a little bit independent of your ballbot, but the concepts are the same concepts used in your ballbot. So we're going to go over control, mostly PID today and its concepts. We're going to do a MATLAB example. That's going to serve as your quiz for the week. So we'll get to that. Announcements. I think everybody's done the t-shirt form. If you haven't, it's the last chance. So if you guys want to work on your ballbots, like are the bins like in a place where you can't access them? Is it locked?
No,
it's open. Okay, so you guys know you can get your ballbots and use them at any time. You can even take those bins home with you if you want. Like we don't need them to stay in that room. It's just for you, whatever's easiest for you guys. We just need you to not lose them. But luckily they're big enough that I think that's going to not be too difficult. Yeah.
Makerspace, I was there late last night, and the Makerspace does lock at some point. So late at night, you can't get in there.
Yeah, the Makerspace does lock. It has hours. That is true. Right now, I think that's the way it's going to work. I don't know if it's safe really to do it a different way than that, but I would love for the Makerspace to be open all the time. But there's sort of safety issues. Yep.
What are the hours for, by any chance? Do you know them?
Excuse me?
Do you know the hours for like the makerspace?
No.
That would be this.
Like I think the syllabus has a link to where that information is included. It's relatively early, I think. Like more like regular business hours, but I could be wrong. Or maybe that's when it's staffed. It's locked at like 8. I can't remember. But you guys, I mean, it's somewhere. You can find it. Midterms, grade next week. My general impression, we haven't graded them yet, but my general impression from talking to people is that you guys, I think, did not do as well as you wanted. That's sort of the vibe I'm getting. So I have a couple things to talk about that. One is I think that exam from a content perspective was fair. I don't think the questions were beyond from a difficulty perspective, but it was long. So there was sort of a time issue associated, and the more familiar you were with the concepts, the faster you'd be able to move through it. So it may have been too long. I'm not quite sure. We'll know more after the exams are graded. But I was happy with the exam from a difficulty level, but I think maybe it was too long, but we'll see. I generally got the impression that you guys felt like you didn't do well. For class grading, to kind of if we get the midterms back, let's say the average is like a 50. So the way we're going to do classes is the grading is you should reference yourself against the average. So none of the assignments will be curved until the very end of the class. So the very end of the class, the grades will be a distribution. I will move that distribution to probably an 86 or 87 will be the mean, and then the standard deviations will push that kind of above and below. That's sort of what I'm imagining. And then I would also like scale that distribution if it needed to be scaled. Usually it doesn't. Any questions about that? Okay. So don't panic. You see your grades. All right, this is where we are. This is pretty cool. I like this slide because it shows kind of everything we've done. And it kind of, I think, hopefully like begins to put this whole problem of designing, making, and controlling robots kind of in perspective. And we've done all these new things, and now we're kind of talking about control. We're going to mostly talk about what I'm going to say is low-level control. Low-level control is really like, or what would you say if I say, we're going to talk about low-level control, what do you think its job is? Sort of on the screen. What is the job of a low-level controller? Really has one job. 461, Riggs 460? What is the job of a low-level controller? See if I can give you help. What is the job of a low-level controller? Yeah.
Wild guess. The controller should track the reference trajectory.
It tracks references. That's its only job. So like you give it a reference, its job is to track that reference. What that reference is changes. That changes the type of controller it is. What you're controlling changes. That changes how difficult it might be to track a reference. But the game is track a reference signal. So let me describe that differently. What is the job of low-level control? Track a reference. Trajectory. What are some examples of tracking controllers? I have four listed. Let's see. Yeah.
Cruise control.
Cruise control. That's this one. So it has a reference velocity that it wants you to track. It has to reject disturbances that might occur to the vehicle. What's an example of a disturbance that might make tracking a reference of cruise control difficult? Yeah.
Adaptive cruise control, then like if there's a car in front of you, and you will like, if you continue on that trajectory, like you'll collide with that car. So like you have to slow down potentially to not.
Yeah, so what's going on there, so there's cruise control, which is tracking a speed, and then this kind of thing, adaptive cruise control. It's really tracking a distance. Tracking a speed as a reference, it's basically constant. Tracking a distance, it's going to be changing. So for this particular like thought example, let's stick with just the regular cruise control. What makes regular cruise control hard? Turning can slow the vehicle down. Hills. So like inclination, air resistance, those things are going to make it challenging for the controller to track its speed, so we have to wrap a control loop around it. What are some other examples? Yeah.
A position controller?
Yeah, let's say like a robot arm needs to follow a position trajectory. A lot of robots are in what's called position control, so that's their job, is to follow motions really, really carefully. A lot of automation is about picking things up and moving them and setting them down. So there's a lot of control around the position of a machine. That's a great example. How about another one?
Autopilot.
Yeah, that's a more complicated version, you know, on an airplane. Yeah, so that would definitely be one. It would be more complicated. Let's stay back from that because that has a lot going on in it. How about an exoskeleton? That's the stuff we work on. If you wear an exoskeleton, it has to provide assistance to you. That assistance probably wouldn't look like a position. That assistance would probably look like an effort or a torque or a current. So position control is really common. The other common version is torque control or force control or current control. So we'll say an exoskeleton. That provides assistance. This is torque. How about, one more, different domain. How about your thermostat in your house? So that has to keep your house at a specific temperature. That's a closed loop controller. Just in the thermal domain. Okay. So now I want to expand this. I want to say not only should it track a reference, but a perfect controller acts like unity, acts like one. If the controller, so now we're going to say like let's talk about block diagrams. We're going to represent these controllers a little bit. We're going to input a reference trajectory. It's our reference we want to track. And then the system's going to do something. Ideally, it's tracking that reference. And we have our reference, our input, our actual, our output. What goes on in there? Yeah.
Usually a controller in a plant.
There's a control law. If I wanted to break that up, the plant, what does a plant consist of? Consists of two things. Yeah.
The feedback loop?
Feedback loop is also, yes, one of these. So there's four things I want to say in here. I'll put feedback here. So feedback. So I'll say the control law is a math function to describe effort. Feedback is the output variables that are used in that math function. then there's two other things. These two things together are called the plant. Yeah.
Physical process?
Process is one, yeah. There's a process and the actuator. So the actuator is what's producing the effort. So I'll say the system that produces effort. And the process is the physical system being controlled. Okay. Now, what do I want? So there's things going on inside this block. This is going to be our controller. What we want this reference trajectory to match the actual trajectory. That's a perfect controller. So we want all of these things to create a gain or a multiplier of 1. If they do that, it's working well. You track that? Well, I want this to be times 1. Does that make sense? Okay, that's the game. How can we create a system that creates a unity gain under these different types of situations? Interacting with physical systems, disturbances. So why is it hard to make a controller act like 1? Why is it hard to make a controller act like 1? Yeah.
Usually, difficult to get the transfer function, and on top of that, if you even if you don't have the model, you can still approach it a different way, but like you have to know how to do that with Bodie plots and everything.
Yeah, we might end up going over Bodie plots. We'll see how this goes. I want to say it's hard for it to act like 1 because these systems have delays. They're ordinary differential equations. Those differential equations add delays or lag. So like each one of these blocks is an ODE that maps the input to the output. Let's think of an example ODE. For the actuator. Where would it come from? Actually, let me just write in these blocks real fast. So this is our control law. It's an ODE. This is our actuator. Dynamics. It's also an ODE. Process dynamics. Sensor dynamics. Together, these are called the plant. Okay, so let's say we want to figure out like what is that ODE? What's in that block? What's an example?
PID loop?
No, this is what we're talking about here is the actuator, the physical thing that produces effort. We spent a lot of time talking about that at the beginning of the class. What is this ODE? It would be the coupled differential equations for example, a brushed motor. So that's going to be a set of differential equations that's going to map a controller effort. That would probably be a voltage or a current to actual effort, which is going to be torque. So we would get those equations, the actuator dynamics, from our understanding of its underlying governing equations. How about process dynamics? Where would it come from? What's the governing differential equation that maps an effort to motion? Yeah.
Dynamics equations that we made for the ballbot.
And we have one that keeps coming up. What do we call that? That's common equation, everyone's favorite. Newton's law. Okay. So this equation is going to be a differential equation that comes from Newton's second law. This is going to be a differential equation that comes from the governing equation of the actuator. How about what's going on here? What is sensor dynamics? Does that have a differential equation? Does this seem like it fits with these two? Like, does it seem the same to you, or does it seem different? Who thinks it seems the same? Who thinks it seems different? So sensors their job is to measure something, turn it to an electrified value like voltage or bus communication value. Sensors track very well. So usually the dynamics of a sensor are extremely fast, meaning that this doesn't usually have appreciable dynamics because it's incredibly fast. This would be like, so imagine you have an IMU, you're measuring with your IMU, and that IMU is, mass, and they're measuring deflection of this mass, so they're getting acceleration. Imagine that mass was extremely heavy. The heavier that mass is, the more laggy that signal will be. That's why they're made from MEMS devices that are very small, so they have extremely fast sensing with a really small mass. So people who design sensors, like you can usually neglect that, but it is real. If you look at a sensor data sheet, in the back it'll usually describe these concepts, how much lag it has. Yeah.
Kind of also, like you talked about not wanting long wires because they have like a more capacitance. Is that also like playing in there, or is that?
Not using longer, you say longer wires?
Yeah, I'm not using longer wires because they have like more
Capacitance. That's a different concept that also uses concepts of dynamics, but that would be the capacitance in the wires reduces the fidelity of the bus signals such that the computers can no longer track like what's happening. So that's a kind of a different issue, but it comes from a dynamics concept. Okay, so we're gonna keep talking about this. These systems have dynamics. What did I say, dynamics? How do you interpret that word? What does that mean to you? What does it mean when something has dynamics? Or what is like a common representation of that? Yeah.
It's just like a model for how something changes over time.
That's true. It is that. I want to say it's more specific than that. It's that, but with a constraint. I think what it usually means or implies is that there's derivatives involved, which means there's usually delays involved. So these systems may have dynamics, which implies a derivative in the equation. Do all systems have dynamics or derivatives? Let's think about the governing equation. We're going to say the process is a spring. The actuator effort is a force. And we want to control motion. We want to control displacement. Does this system have dynamics? Do they have derivatives? No. So a spring, if we're talking, it's just the force maps directly to the displacement through the stiffness coefficient. So if I force a spring, it's going to respond infinitely fast. It's going to deflect with the same rate that force changes, because there's no dynamics in here. If we added mass to the spring, and now the spring has mass, then that would add dynamics, it would add delay. But generally in mechanical engineering and robotics, we would say they're massless springs. There's no dynamics here. Yeah.
Actually I know in all physics and dynamics course I've taken, obviously we assume massless springs, but when you're actually modeling systems in real life that require springs, do you also assume it's massless?
Yes. The mass of a spring is usually so low that it isn't worth the complexity. It doesn't really have changed the answer. So if I push on a spring, so I'm pushing on the spring, its displacement, does it track perfectly with the force trajectory?
assuming that the spring is the only like force, but in reality.
Assuming a massless spring is the only thing. So if I push on it, it deflects instantaneously. There's no lag between the force and the response. Agreed? That's only true for certain systems that don't have like derivatives in these equations. As soon as there becomes derivatives, systems start to have lag. Let's talk about that a little more. This is a concept called system dynamics. We kind of touched on it a decent amount when we were doing the initial modeling. And it comes up more because control is really a ton about controlling the systems, and the system dynamics play a huge role in that. In addition, controllers have their own dynamics and can be thought of through the same lens. So that's kind of why this is coming back up. It's really, really important in the concepts of control. If a system has dynamics or ODEs, it will often have delays. This usually like slows the system down. It can add oscillations. We can view this behavior, this concept, by thinking about or investigating a system's impulse response function. Called an IRF. Who's heard of an impulse response function? How have you heard about it? And what did they say about it? Or what do you recall?
I mean, you can use it to like completely reconstruct like your signal response based on that.
That's right. So I would say my version of that is systems are fully described. It's not how you spell described. By their IRF. The IRF, impulse response function, is literally the system's response to an impulse. So now what I have here is an example. That would be an impulse function. So it's 0, it has a value of infinity at time equals 0, the area of that impulse is 1. So this is our impulse function, and now the question is like, what can we get by that? What can we get from this? What understanding can come from this? So imagine we have a mass spring damper system and we hit it with a baseball bat. That is essentially impulsing it. Does it make sense that you would see a response that might look like this, might look like this? Yeah? And the only difference between these would be the exact coefficients of those parts in that mechanical system, but these are both viable impulse response functions. Agreed? These are the delays. So this impulse, it gets delayed and spread out over time. This impulse gets delayed and then becomes an oscillation. It's because that these do not track this perfectly that adds challenge to control. It's because we have to compensate for the dynamics of systems, because they don't track perfectly on their own. They have these properties that spread the delay and spread the input out over time. What can you do with an IRF? Does an IRF have like a special use? Anybody know? You probably learned it in 260. So let's say you have a system and you have an input and you want to know the output of that system. You want to know what happens when I take an arbitrary input, maybe not this input, but an arbitrary input, and I provide that input to the system. How did I get this? How do we get these values? Where does this come from? This comes from the impulse response function being involved with the input. Convolution is the math tool we use to do this. We're not going to learn that, but that's why IRFs are so important, is that they are the tool to find the response in the time domain. Do they work in the frequency domain? Do we know like what is the frequency domain analog of the impulse response function? You know?
I should know this.
The system's Bodhi plot or transfer function. If I take the Laplace transform of its impulse response function, that fully characterizes the system in the frequency domain. So we have like the frequency domain part you don't have to worry about for this class. We're not going to talk about it, but for those who know it, yes, the frequency domain and the impulse response function are related by the Laplace transform, and they're both key to finding the output of a system. Just whether you use one or the other depending on whether you're operating in the time domain or frequency domain. Okay. So what this has told us is systems have delays. Those delays come from ODEs. We describe those delays using an impulse response function, where that helps us gain insight into the system. And an impulse response function is a key tool to predicting the output, which you won't really have to do, but I just want you to know that. Okay, so this is our block diagram. I kind of want to go through these, like what these are. A control law is the ODE. I think you guys might know this already. Like this is kind of like just re-going over the same thing, but I think you guys are tracking it. Do you want me to go through these? It's sort of the same thing I was just saying about what these things are. Do you feel like you know what these blocks are? Who wants to see it again? Okay, let's do it. The control law is an ODE, potentially, or not, but it's an equation, math equation, that typically operates on the error. In this block diagram, we have our reference trajectory. We're going to subtract our reference from our actual value. That's the error. So that means like we wanted to be here, we're actually here. Now we know we're off by some amount. We're going to operate on that error as a set of instructions and then create effort to try to correct this error. That's the general strategy in control. We're always operating on error. We're going to create a strategy here that's just going to try to drive that error to 0. So control law is an ODE, an equation that operates on the error, often includes derivatives. The actuator is the ODE that describes how controller effort maps to actuator effort. Is actuator effort a physical, a real thing, or like a thing that exists in software? It's a real thing. Like it's actually going to be effort provided by the actuator. It's going to be torque or force, typically. The controller effort, is that a real thing, or is that something that exists in software? Software. I'm going to say it's both, because controller effort will be computed in software, but you'll also have something that you're sending out. A PWM signal, a torque command, a duty cycle, you have some physical thing that's going out, and then error. Software, that was only software. It only exists. You're going to compute it, you're going to operate on it, and then that's it. This is a real thing. Actually, your output is a physical thing. This is the measured version of it. Yeah.
So going from the controller effort to the actuator effort, is that encapsulating like all of like taking whatever the controller like PWM or whatever like the controller gives, converting that into like let's say a voltage and current to like give to the motor to like move it, which will like cause the torque to, or the force to happen?
It would be the actual voltage or actual current. This signal would be either, usually it's a PWM signal, so usually it's a voltage value that's changing here. So the controller effort would be a voltage value that changes.
So that kind of does that beforehand almost, and then the control, like the actuator system receives it and then converts that into the actual torque or whatever.
Yes, the controller effort will say it receives as a voltage. It has to convert that voltage into an effort. So that would be coming from Kirchhoff's voltage law and your motor equations. That converts, in that equation is information that converts voltage into torque current. So the control law is software. The actuator system dynamics is a real physical thing. The physical system is a real physical thing. And the sensor is a real physical thing. And the error is something you compute in your software, but you won't actually see it. Physical system, this is our ODE that describes how actuator effort is converted to motion. My iPad just restarted. Let's give it a sec. I can't actually use it right now, but the sensor is going to be the ODE that maps the actual change into the real change, or the real change into the measured change. While that's going, I'll just switch to my actual notes. And hopefully it'll come back. Oh. Yay! All right, we're back. Okay, we lost the physical system. ODE that converts actuator effort into motion. Yeah.
Can an ODE just be any differential equation, or is there specific like parameters that describe it?
That's a good question. I think I think you can generally think of it as specific parameters. Although like that'll be a good enough approximation, I think.
Are there like certain differential equations that classify as ordinary differential equations
Definitely,
though?
that's a class of differential equations, but if you're thinking about what do they represent, what do those dynamics represent, they might represent a set of dynamics that can be easily described by an equation. It might represent something that's not so easily described by an equation, something that really exists as a function, as a frequency response or an impulse response function only. ODE is the sensor, or sensor is the ODE that describes how the output is measured. You really think of an example that like illustrates how sensors can have dynamics. How about a microphone? Or a speaker. We'll think of a microphone, it's a sensor. So a microphone senses vibrations, and sound vibrations convert that into a voltage and stores it. So imagine at some point the mass of that microphone system, which will be a coil and a magnet, the mass of that system will start to eliminate or be slower than potentially what is being heard by the microphone. So like let's say you have a regular microphone, we have a bunch of bats in here, and the bats are sort of like emitting ultrasonic sounds. Would this microphone pick it up? No. because this microphone is designed to have a bandwidth or available frequency range of human speech and sounds. So things that are sufficiently high, this microphone wouldn't be able to pick it up. Its system was not designed for that. It would lose it. It would lose that ability to hear that because the mass inside this microphone sensor would be prohibiting that high of frequency. Does that make sense? Does that kind of help? Where did this come from?
Would you consider like in an IMU having like the spring damper systems like that measure the displacement? Would that be considered like the dynamics of the sensor as well?
Definitely. Yeah, same exact concept. Anything that has mass is going to eventually have a bandwidth issue. Okay. So let's kind of like go back through this. The objective of our controller is to track a reference. It does that by driving error to 0. If error is 0, what's the gain of that system? 1. So anytime error is 0, the system has a gain of 1. Agreed? It's doing its job. Anytime error is not 0, the system doesn't have a gain of 1 and it needs to catch up. Make sense? Control laws are functions of this error signal, E of t, which we're saying is the difference between the reference and the actual output. Everything's going to operate on that error. In lab, we talk about a proportional control type, where we mapped the effort of the balanced controller proportionally to its lean angle. And that made it was easy to do that because it was trying to track a lean angle of 0. So all we had to do was take a gain, multiply it by your lean angle, and we got our controller effort. That was proportional control. There are also other types of control. We're going to go over the most common type ever, which is called proportional integral derivative control, or PID. And the controller effort for PID is the sum of 3 terms, 1 for each. Let's look at how these terms are created. Who's very, very comfortable with PID already? Okay, cool, about half the class. That's not surprising. That's okay, it's a really common concept. But for those of you who are not as comfortable, we're gonna go through it. Okay, so we have our block diagram up here, like we talked about. I've defined a couple of variables, error being E of t, the reference trajectory being R of t, and the output being Y of t. Okay, so the proportional gain, the term for the proportional gain is just this. The U is, we're going to say, is our controller effort. So UP is the part of our controller effort that comes from the proportional term. It's going to be KP times the error, just like we talked about for our ballbot. The error may be, if you're not referencing 0, you'll have to have 2 terms in there. It acts like a spring, a virtual spring in position control. So that should kind of help you understand if I have a controller that's doing position control and its reference is here and I deflect the system, it's going to kind of try to bring it back. It's going to drive that proportionally. That's going to come from this term. The integral term is the integral of the error scaled by ki. So the u of I, or u of t, this is the controller effort from the integral term. It is ki, its gain, times the integral of the error term. A couple questions for you. Who knows what the integral term is typically used to do? Yeah, what is it?
Steady state error.
Remove steady state error. So if there's steady state error, what this term will do is start to sum that error, build it up. It's going to sum that error over time, and eventually it's going to drive it such that there's no steady state error. That's kind of what integrals is for. It removes steady state error. One thing to keep in mind for integral gain, for your integral term, any area Like if you want, let's say you want the integral effort to be 0. If it starts tracking a reference trajectory and deviating, any area between the reference trajectory and the actual trajectory would have to be removed by going over the trajectory by the same area. Does that make sense? So like this term can have components of it that persist for a long time. It will make the net area over the terms eventually equal to 0. But whatever is below the reference trajectory will end up having to be above it if we want that term to be removed. And then lastly, we have the derivative term. So this is our controller effort from the derivative term. It's our KD, the derivative gain, times the derivative of the error signal. What does that feel like?
Usually feels like a force that's slowing it down if it starts moving too quickly to the correct position.
Yeah, it's going to slow you down. It's typically a virtual it can be thought of as a virtual damper in position control. So if you have this getting on and you try to move it, it's going to fight you like a damper would. It's never used alone. Why aren't derivative terms used alone? Yeah, they actually don't provide effort to send it to the reference, but they help remove oscillations. Who's used a D term in an actual controller before? Did you know what was like? Was you notice anything that could be particularly an issue with this term, particularly in the real world? Yeah.
Signal can
Yeah, so this comes from a numerical differentiation generally. So if you wanted to calculate the derivative of the error, it would be common to save the last error. Then when you're in this control loop, take this error, subtract it from last error. That's your error difference, divide by the time. Like that's a common 2-point numerical differentiation. So that can add a ton of noise. So this is susceptible to noise. Because it involves a numeric differentiation. If you turn your D gain up too high, you'll typically hear it or even see it, but it will go like as you hear that derivative being taken. So this one kind of has to be used with care. Okay, this is a quick little example for us to do. What I have here is an example reference and an example output. What I want you to do is build the 3 controller effort terms and then create the total. It will take like 2 minutes to do this. So we have I'm going to try to get to this mallet example. I think we'll get there. I think we should do this. So I want you guys to create these. You should have like 3 different curves. Those curves sum to a curve there, and we can talk through it. So this will just take like 2 minutes. I'm just saying, think of these gains as 1 for this little example. Yeah.
So RFT is what we're trying to do and YFT is what's actually happening, is that correct?
Correct.
Okay.
So RFT is your reference, Y is your output. Everybody should do this. If you cannot do this, then like that would be an indicator that we're not where I want us to be. I'm hoping this would be relatively straightforward for you.
Start at zero.
I have the same.
I'm literally thinking.
And then it's just another linear.
No, this is, yeah, that was of course, but that's not like.
Yeah, except I don't think it starts flat at the bottom, it goes to the edge because it's the linear.
It's not just the sum of these.
Okay, let me go through with you. Actually, you guys can help me do this.
It's like discontinuous.
What is the equation, like who got this and how did you get it?
The error is just going to be r of t minus y of t. Since y of t is a constant that's like really low, it's essentially just going to look like r of t.
That's right. So it's gonna look something like, cool, that's all we did, r of t minus y of t. It's because y of t was conveniently chosen, basically 0, then we make this very straightforward to find e. Then how do we calculate the integral of e? Or what did that look like? Over.
Looks like when e of t is increasing linearly, the integral of e of t looks like it's increasing exponentially.
Mm-hmm.
And when e of t is constant, then the integral of e of t looks like a linear chain.
Something like that? Yeah, agreed. Okay, how about the derivative of error? What does that look like? Somebody on this side of the room. Constant, 0. Yeah, so then what did u of t look like? On this side of the room. Does anybody draw it? Somebody want to come up here and draw it? You want to come up here and draw it? Yeah, go for it. Yeah. And then talk us through like how'd you get it?
So I had something like that.
Mhm.
So this first half is like the D term is like steady, so that's why it doesn't start at 0. It starts like where D starts.
Mm-hmm.
Then I kind of just combined these, but I tried to make it like look a little steeper than this. It doesn't look like that, but that's the plan.
Yeah, so this would be the combination of the purple and the blue. It's gonna make something like a parabola, but a little steeper, and then drop, and you have that linear increase.
Yeah.
Yep, that's right. Awesome.
So this is assuming that like none of this is actually being applied to the system.
Correct.
So like theoretically though it wouldn't really look like this in reality because you would have been applying feedback to it
Yeah.
for it to rise up.
Yeah, this is an inverse simulation. In actuality, it would be forward. So this, the u of t would have an effect on y of t. And that effect would have to go back into this calculation, but for this example, we're not talking about that. Does everybody track what PID is, kind of where it comes from, how maybe you would implement it? Let's talk about how we would talk about how good it's doing, how well your system is being controlled. Okay, so coefficients, your PI or KP, KI, and KD have to be adjusted, and that process is typically, it's called tuning, and it's done iteratively. It's done often, or maybe not always, but often done using a step response. A step response is the system's response to a step input. For those of you maybe who haven't seen that too much. So it's just a really common way to assess how well a system can track a reference because it's high frequency, it's discontinuous, there's an immediate jump. So that helps you see like how well your system responds, how quickly it responds. And then you can see it kind of settle out. A step response would be sort of similar to or analogous to an impulse response. There are these classes of responses that are used over and over in system dynamics. Step response would be one of them. We're going to use it to view our system and how well it's tracking. So adjusting our controller parameters, KP, KI, and KD, are done, you call that tuning. You can assess them in the time or frequency domain. This class will talk about the time domain. The way we would assess a system, how well it's doing, is by these kinds of variables. Rise time, the time it takes to reach 100%. Settling time, the time to reach 95% of its final value. Percent overshoot, the amount it goes over top of its steady state value. Steady state error would be the difference between the reference and the actual value at time equals infinity. These are the kinds of things that we would use to talk about how well our system is doing. This is our vocabulary for assessment. How fast does it rise? How fast does it settle? How much overshoot does it have? Oftentimes, if you're building a robot, you're gonna have some goals for this. So these things will usually, these constraints, what do you want for this, will typically come from you. You might think of an example constraint that you might see when solving a problem. Yeah.
One example I've had with working with the robot was we were doing shooting, and we needed to shoot a lot of balls very quickly, so we needed to have a really quick ramp up speed with a very low percent overshoot because we needed to be going the correct speed.
Yeah, those are the kinds of constraints that you would have in your application that would guide you on what to do here. Oftentimes, it might often be you want it to respond as fast and as true as possible, and that's kind of a common goal. But let's say you're building a robot that interacts with people, position-controlled robot moving in the world. If it's going to be close to people, could you tolerate overshoot? Probably not. So there are other application-driven factors that would potentially come into this. This is our example KP response. This is from our lab slide, but I'm just showing for a system, if I increase KP, we see its step response get closer to the actual value goal, which is here. So this system has a lot of steady state error. Yeah.
So suppose that we do have a KP, is that term not calculated for when time is 0? Where things happening?
No, you still can.
Because the derivative seems to be undefined at 0 when it steps up.
Because these systems are digitally sampled, it would only know that something had changed between two control loop iterations. So the fastest response you could ever sort of see would be a response that discontinuously jumped on one control loop iteration, which would still be able to have its derivative calculated. So let's say we have a D term, and let's say I give a system a step response. What's it gonna do? Let's say it's only a D term. Say I give a system with only a D term a step response. What would happen? It would basically kick forwards, and then it would stop. You would see that discontinuous jump as a kick forwards, and then that'd be it. Yeah, cool. Okay, so let's talk about how you might adjust these parameters. We've talked about these controllers. They need to ideally create an overall system gain of 1. That's challenging because of disturbances and delays or dynamics in systems. So we created this control law that had to do with driving error to 0, which would indeed make our system gain 1. But now we need to know, how do we actually tune the coefficients in that control law to drive error to 0? There's no right answer to this. There's common best practices, which that's what we're going to learn, but there isn't really a right answer to tuning a PID controller. It's really up to you. The most common control tuning strategy is developed by Ziegler-Nichols. If you're interested in knowing that, you can click on that link. It'll take you to the Wikipedia page. We're not going to learn that formally. I'm going to kind of give you the Cliff Notes version. So when I'm tuning a PID controller, there's usually 3 steps. Does anybody know the first step? Anybody? Yeah.
Start with the B gain and get it to kind of rise up to the point where it at least hits the target whatever it's called, I forget.
Reference?
Yes.
Yeah, so that's right. So step 1 is increase KP. And I'm gonna say increase it as high as comfortable. What does that mean? Why does it say that? Yeah,
Because as you get a higher KP, you're gonna get a giant overshoot. So if you're, say, tuning a shooter, it's gonna go way above, so you don't wanna have an uncomfortable amount of speed on your audio.
and what's happening as you see more and more overshoot?
Right, extreme decrease as you're trying to go back down to.
Say it again?
If you have an extreme overshoot, you're gonna have a huge peak, and then you're also gonna have an extreme drop back down as you go try to get back down in the air, because it's gonna try to the P term is now gonna be working in the opposite effect and trying to actively slow down.
All of what you're saying is true, but I'm trying to highlight something I think that's like slightly adjacent to that. Yeah,
You have a quick rise time.
you have a fast rise time, so basically like your KP is kind of your baseline or kind of first response controller effort. We're gonna tune it as fast as possible. That's making the system stiff. But at some point, it's gonna be so stiff that it will start to oscillate. Those oscillations will begin to persist, and then those oscillations can grow. So at some point, you'll be tuning it, it'll start to overshoot, it'll start to oscillate, it'll oscillate more, and then it'll go unstable, which is like, output will run away from you. That can be very dangerous. So that's why I'm saying tune it as high as you're comfortable. The goal is crank the KP as high as you can. So the way that it's explained, I think it's Ziegler-Nichols, is bring it up to instability, but not quite there. So you want to go right up to where it's unstable. I'm saying just go as high as you're comfortable. But that's what you do. Keep increasing KP. That's you'll start to see the system responding well. But it'll have things like steady state error and oscillations and overshoot. Okay, step 2, reduce KP. You can reduce it, like Ziegler-Nichols will have like a factor that you reduce it to, like 0.6, I think. But I'll just say reduce it till you feel comfortable. And then add KI to remove oscillations. Oh, wait, no, steady state error. So you're gonna tune KP, you're gonna watch it get better and better, you're gonna get a little scared, so you're gonna back it off, and you're gonna increase KI, and you're gonna see its steady state error go to 0 very quickly. Now you have to handle these oscillations if you don't like them, yeah.
What's the point of taking KP all the way up and then just immediately bring it back down? Why not just go straight to what you think is fine and then go on to the next step?
Because of knowing, this kind of helps you to actually know this. So let's say like, once you've done that, you usually have an idea of like how much error is produced, how much effort is produced. So you kind of begin to see what can your system take? Like how much effort can it take? Like I would do this even though I would do this even though I know I'm going to reduce it. Just to kind of see how the system responds, get an understanding of how much effort is going into that response, then I would add it. But you could shortcut it if you want. If you get proficient in this, you probably would shortcut it. Step 3, add KD to remove oscillations. By driving error to 0, the system behaves like 1. Okay, so now I want to go through this like little chart. And I want you guys to tell me what the answers are here. So I'm going to talk about increasing KP, increasing KI, and increasing KD. I want you guys to tell me what is the effect on rise time, overshoot, settling time, and steady state error. Not all of them have like a strong effect on all the parameters, but we'll kind of do it together. Rise time. What's rise time? How quickly it passes its desired value. So if I increase KP, what happens to rise time? Decrease. If I increase KP, what happens to overshoot? Increase. What happens to settling time? Yeah, it does increase. I'm going to say small increase, but it does increase, but not as fast as everything else. Steady state error. If I increase KP, what happens to steady state error? Decrease. It decreases. How about KI? Does that make sense? Steady state error. So imagine a KP, you can, like, let's say this is our target, then we could say that a KP is essentially a spring connected to this target to where I actually am. So as I increase KP, that spring's gonna draw closer and closer. Will it ever reach? No, it wouldn't. So a P only will never have zero steady state error. Ki, if I increase Ki, what happens to rise time? It's gonna decrease. So if I increase Ki, it's gonna start to see that error, the difference between the reference and the actual. It's gonna integrate that, and it's gonna start to drive a controller effort based on that area. So that's gonna reduce the rise time. It's gonna increase overshoot. In fact, it increases overshoot a lot. Because it has to get above and below the reference to remove that. So it's gonna keep doing that. It's gonna increase the settling time because of that concept. So it's basically gonna totally eliminate steady state error. How about KD? If I increase KD, what happens to rise time? I'm gonna say small change because it's like there actually can be, it actually has two factors. It'll be a kick forward and a kick back. And those two things would sort of negate each other. So it's really gonna end up being a small change. What's gonna happen to overshoot? Decrease. Settling time? Decrease. Steady state error? Yeah, no, not a small change, no real change. Great job. We have kind of one more slide. Then I think I have my MATLAB exercise. Yeah, so then I want to show you a MATLAB exercise. This is my last slide. Okay. This is kind of a quick little aside on reference trajectories to make sure that we're all on the same page. So what it is, the reference trajectory that you have, the more complex that reference trajectory is, the harder or more high performance the controller task is going to be. Oscillating references are harder to track. The faster a frequency is in the reference, the harder the system is to track. Does that make sense? So this one, the blue one on the left, this is easier. This is harder. The faster it oscillates, the harder it is for the control system to track. Sometimes references are static in some systems, like a thermostat, or cruise control. Those systems are called regulators, special name. What's our reference trajectory in our project? Constant so far, constant of upright. We might end up modifying it, but is it gonna be a high frequency oscillation of any kind? No. So how good do we need this controller tuned?
Not aggressive.
We don't really need to follow a high frequency, but we do need it to be high fidelity, even even at low frequencies and low amplitudes. So we actually still need a high performance controller, even though we're not tracking a super fast changing reference. Our reference can change discontinuously, kind of oscillate around zero, so we want to be able to track that really well. Okay. I just want to see if this makes sense to you guys. Let's say I'm trying to track this reference. And I can't. The controller isn't fast enough. What will happen? So let's say this is my reference. What will the output look like if I can't track it well? It has like two important attributes. Yeah.
Might kind of look like that's cosine, it might look like a sine wave, like kind of off shifted, because as it's trying to speed up, it would be trying to get up there because it's a little bit lagged behind, and then it's gonna already be decreasing when it finally gets up there and it becomes too late.
Yeah, that's so I'm gonna call what you said a phase shift. So it's gonna have a phase shift on the output, and then you alluded to it to the other part. What's the other thing that's gonna be different? In what you were saying, we didn't directly say it.
It won't be as tall.
The amplitude will decrease. So let's say, I'm just gonna draw this on here. Let's say I'm trying to track this. and my system is not doing well, it probably would do something like this. I'm gonna have it start at 0. Oops. Something like that. I try to draw phase shifted, reduced sinusoid. So hopefully it makes sense to you that if I give it this blue reference and the system is not tracking well or the frequency is too fast for the system to track, what we're going to see is a reduction in the amplitude and we're going to see a phase shift of the sine wave. Agreed? Okay, that makes sense?
Yes, but is the output necessarily a sine wave or could like weirder things happen because it's just really bad?
If the input is a sine wave, the output is a sine wave. That's a property of a linear system. In this class, we'll focuses on linear systems. Okay, so that's kind of what's going on here in this last bullet. The output should closely match the reference, but at high frequencies, the amplitude will begin to attenuate, and the output sine wave will be delayed. And this is kind of the downstream effect of the system dynamics that we talked about in the beginning of the lecture. And there's a ton of kind of technical infrastructure around assessing these concepts, these are frequency domain concepts, which we may or may not talk about, but there's tons that goes into this. So just knowing that this is something you might observe, this is something a lot of people care about in robotics, that's probably good enough for this class. Okay, what I want to do now is talk you through an example of the PID example that I wrote up in MATLAB. And I'm going to tune it with you real fast, and then we'll see if we can have time to do it first. So now, for right now, just hang with me. Don't get out of your computers. Okay, so this is uploaded to Canvas. This is a file that creates a plant and then creates a few different controllers. A P controller for a few different P gains, a PI controller, and a PID controller. So for now, I'm just going to run it and we're going to kind of talk about it. What this M file uses is a Laplace domain representation of system dynamics. You don't need to worry about that. That's not part of this class, but it's convenient for creating these responses. So let's run this section. So this is plant. This is sort of creating the system that's going to be controlled. And it should plot so this is the impulse response of that plant. Okay? I'd like for you guys to know, or to get a kind of a general feeling of, you see an impulse response, kind of what that means. So this is saying you can get some understanding of the system by looking at how it shifts and delays following an impulse. So I have it plot its impulse response. That's the impulse response of the plant. Here we're going to do some proportional control, so I'm going to run this section. It's going to do 3 different controllers they're all KP, so they're all P-only controllers. But it kind of shows how the system, as I increase KP, the system gets closer and closer to the actual value, but it starts to oscillate more. Make sense? Is he tracking that?
Are we controlling to 1?
Yeah, step response goes to 1. Unless you scale it, the step response is defined to go from 0 to 1. So if you wanted to mess with those, you would just edit those here. Those are proportional gain values. You can change them. Just keep in mind that I hard-coded them into the title, or into the legend. So if you change them, just know your legend will be wrong. This is our proportional integral term. So this shows one of the P controllers from last cell, and then the addition of the I controller, the I term. So you can just see the I term immediately removes that steady state error. And it rises a tiny bit faster. Make sense? Now let's try PID. So that's the last cell. I have them all as 0 right now. So what I want to do with you guys is sort of like tune it for a minute. And then up in the top, in the definition of the plant, there's a bunch of things that say inertia, uncomment for exercise. I want you to comment the inertia that I'm using and uncomment this inertia, and do that for all the parameters that are shown. So I'm basically changing the plant and having you redo it. That's the game. So before we do that,